Hi, in this video I would like to go over the material that we were not able to cover due to the hurricane. So I believe we had already started this topic, gradients. So I think it best to just start from the beginning of this topic once more. If you're given 2 points, like these shown here, and asked to find the gradient of the line segment connecting those 2 points, well, all you have to do is find a ratio. And it's the ratio of what? The change in the y coordinates to the change in the x coordinates. So when you're working with change, it's always defined as some final value minus some initial value. And so the situation may dictate which is the final and which is the initial. However, in an arbitrary case like this, you could pick any point as your so-called initial and so-called final. So if we take this point as the initial point, let's just say, and this is the final, then the final value of y will be 40 and the initial value of y will be minus 20. Notice we have parentheses and the minus 20 in here. You do not absolutely have to put these parentheses, but they help to you focus on what you're supposed to be doing. Right? Sometimes students forget that it's minus a minus and just put minus 20, and then that's a mistake. Notice if this is the initial and this is final, then down here we have to apply, you have to be consistent. So this is the final value, it's the final value of this is initial, this is final, so it's the final value of the x coordinate minus the initial value of the x coordinate. So as you can see here, the final value of the x coordinate was minus 5, and here the initial value is 10, so final minus initial, and of course we get minus 4. Perhaps it would have been more in keeping with something that you would naturally do to call this one initial and this one final. So for the most part, we pick the leftmost point as the initial and the rightmost as final. For the most part, that's not a rule. And so here then the final is the final value of y minus the initial value of y, so that's 20 minus 40. Be careful, it's a minus 20. It's a minus 20. Right, the y value is minus 20 and the final y value is minus 20 and the initial y value is 40. And then here we have the final value of x is 10 and the initial value of x is minus 5. One major point to carry away from this is that it doesn't matter which of these two you pick as your initial or as your final, you'll get the same value for the gradient. But you need to be consistent. If this is your initial and this is your final, then this has to be your initial value of y, and this has to be your final value of y. This has to be your initial value of x, and this has to be your final value of x. So just be consistent, right? So for example here, you could not have said minus 20 minus 40 and then put minus 5 minus 10, because you have already decided that this will be your final value of x, so then this has to be your final value of y. Okay, and so that little division there gives you the gradient. So remember that the gradient gives us a rate, right? It's telling you how quickly one variable varies with the other. So this is applied in many different situations, in engineering, you know, in the various sciences, in finance, in economics. You know, you can look at the rate. You might be interested in the rate of how quickly, for example, the cost of producing an item varies with the amount of items you're producing, or the number of items you're producing, I should say. All right. So later on you'll see how all this is applied, and so on to then just try and get the idea, so that wherever it's applied, it's just, you know, something that makes sense. So again, the gradient gives us a rate, and it tells us how quickly one variable varies with the other. So what's going on here, and then it's telling us that the y variable decreases 4 units for every 1 unit increase in the x variable. So make sure you understand that. So for each of the following, state the sign of the gradient, calculate the value of the gradient. So I'll do a few of them. So for this one, the gradient will be positive. So one easy way to look at this is to always take the leftmost as the initial. Right? And so if the leftmost point is the initial point, then just ask yourself, then does the y increase or decrease as you go to the other point? And so for in this case, the y decreases, so this is a negative gradient, the y increases, so this is a positive gradient. The y doesn't change, so the gradient is 0. For this one, the y increases. Notice this, if this is your initial point, then the y value, the final value of the y coordinate is greater than the initial value of the y coordinate. Here, the final value of the y coordinate will be less than the initial value of the y coordinate. Notice the initial value of the y coordinate is this value here, which I believe is 1, and the final value of the y coordinate is -4. Right, so that's a decrease. Right, so then this is a negative gradient, and likewise this is a negative gradient. And then to calculate the value, well, we need to find the change in the y and divide it by the change in the x. So let's take a look at this one here. Let's just do this one here. The change in the y is going to be equal to -2 -4. And so I only use parentheses to just keep me focused, right? And so then this gives me then -6. So that means there is a negative change in the y, right? There's a decrease in the y decreases. And of course, since we're always taking the leftmost as the initial, the delta x will always be positive. And so delta x here will be what? The final value of x for this line segment is -5. And the initial value of this segment is -7. So then this is 2. Obviously then the gradient is delta y over delta x. So that gives us -6 over 2. That gives us -3. So the gradient is -3. Right, and let's take a look at this red one here. All right, and so if you look at this line segment here, delta y, it's the final value of y, which is 1, 2, 3, 4, 5, minus the initial value of y, which is -4, and that gives me 9. And then the change in the x, it's the final value of x, which is 1, minus the initial value in the x, which is -2. And of course then this gives us 3. And of course then the gradient, delta y divided by delta x, and the symbol often used for the gradient is m. So this gives me 9 divided by 3, which gives me 3. So now we look at a different question. Now we're looking at finding the gradient on a function that's not a simple straight line. So we're given this function f of x equal x squared, and we're asked to find the gradient. That's what the rate of change is. We're asked to find the gradient when x is 2, when x is 7, and the average rate of change in the interval from 2 to 7. So notice here, we have these 2 points on our graph. So how would we get the instantaneous rate of change here? Well, normally what you would do, as you did in high school, you'd maybe plot this on some graph paper and you draw a line tangent to this curve here and measure the gradient of this line. And if you were to do that, you would get a gradient of 4. And so the gradient, and so that would answer this question here. The gradient, the rate of change when x is 2 is 4. That's how steep this line is. Of course, here you would expect the line to be steeper, the tangent line. And if you were to carry this out, you should get a gradient of 14. Right. Now when they ask for the average rate of change, then you draw a line between the 2 points. So that's always a secant line. So remember that instantaneous rate of change, it's a tangent line, and the average rate of change is going to be a secant line. And that's a secant line here, right? A line drawn between these 2 points. And when we just find the rise over the run, the change in the y over the change in the x. So the final value of y is f of 7, the initial value of y is f of 2, the final value of x is 7, and the initial value of x is 2. So when you do this, you substitute 7 in this equation and then 2 in this equation, you get 49 and 4. that gives you 45 over 5, which is 9. Now you may be tempted to say, well, okay, I can find this average by simply finding these two the rates of change, instantaneous rates of change here and here, because this is 4, this was 4, and then here the rate of change was 14, and of course then 4 plus 14 divided by 2 gives you 9. But that will only work for functions of this type, so don't do that. You know, when you want to find the average rate of change, think in terms of the secant line. You're going to find this the gradient of this line connecting those 2 points. So we can see that very clearly in this example. If I give you the function f of x equals x cubed, if you find the instantaneous rate of change here, you would get a gradient of 12, and here, when x is 7, you get a gradient of 147. If you draw the line, the secant line between these 2 points, and you find the gradient of this line, remember it's the change in the y divided by the change in the x, you would get 67. However, 67 is not the average of 12 and 147. So be aware of that, right? You can't just simply find this gradient and this gradient, average those two, and that will give you the average, the gradient here. No, you need to find this gradient independently. It don't happens to work for functions of, you know, x squared type functions. All right. So here's a little application. We're looking at a particle, and this particle is moving to the right, and its position varies with time, as indicated in this figure. So notice what's happening here. As the particle moves to the right, it's moving to the right, but I'm recording its horizontal position on the y-axis here. Sometimes students find that confusing because the object is moving horizontally, but I'm plotting its motion vertically. So just be aware of that, right? This is what is called an abstraction, and you have to be able to work with abstractions, right? So so for example, if you want to know where the particle is at time equal 2, you just come here and then you come over to the y-axis here, and that will give you where the particle is. In other words, that will give you the x position. So be careful, right? Don't let this confuse, right? The particle is moving along a line to the right. If you want to know where the particle is at time equal 10 seconds, well, it's at, I think this is 20, 40, 60, 80 meters to the right of where it started. Something very important here to note is that the gradient doesn't change. In this particular case, when we're looking at the rate of change with position with time, that gradient has a special name. It's called velocity. So you will find that not all the time the gradients have special names, but in this case, yes, the gradient of a graph of position versus time is called the velocity. And so for this case, then a person should be able to look at this graph and recognize that it represents a particle moving with a constant velocity. We can find the rate at which the particle's position changes by simply finding the gradient of this line, which is the change in the y divided by the change in the x, which gives us a value of 8. So this particle's position is changing at 8 meters per second. Every second, its position changes by 8 meters. It increases by 8 meters. Here's another example. Suppose we are given that the position of a particle varies with time as described by the function 7t cubed minus 12. These equations might be beginning to look a little bit scary, but don't let that set you back, right? Just work with the ideas. So the question here then is, the questions are, where is the particle at these times? How fast is it moving at these two particular times? And what's the average velocity in this interval from 3 to 5? So I hope you're beginning to get the sense of this, right? To find out where the particle is given this equation, you just plug these values into it. So sometimes that's called plugging and chugging. So I put 0 in here, I get minus 12. When I put 3 in here, I get 177. And when I put 5 in here, I put 863. So it's moving pretty quickly, right? It's picking up speed actually, right? And how do we know that? We can look at the graph of this thing and we can see that the gradient is not changing. So the question now becomes, how fast is this particle moving at time equal 3 and time equal 5? The important thing here is that you know that what you need to do is find the gradient here. And so if you were to do that, if you were to find these gradients here, right? So first you need to know what you need to do, and then you need to know what how to do it. So those are two very important things, but first comes what it is. You need to know what it is you need to do. And so if you were to do this and draw tangent lines here and find the gradient of these tangent lines, you'd see that at 3 seconds the particle is moving with a velocity of 189 meters per second, and here at time equal 5 seconds the particle is moving with a velocity of 525 meters per second. So it's picking up speed very quickly, right? What's the average velocity? Well, remember, we can't simply add these two and divide by 2, right? Especially since you notice that this is raised to the third power. So we find the gradient of the secant line, and that's the change in the y divided by the change in the x. Notice we get, in this case, 343 meters per second. That's the average velocity in this time interval. So I hope you're getting the sense of what we mean when we talk about instantaneous rates of change and average rates of change. So these gradients here are instantaneous rates of change. They're giving us the rate at which this value is changing at these instants, right? Here we're getting an average over an interval. So averages are always associated with intervals, and instantaneous is always associated with a point. Okay, so this video is getting a bit long. I think it's about 16 minutes now, so we'll pause this discussion here and continue in the next one. Bye for now.